Resonance and coupled circuits. In this video, we are going to discuss about resonance and coupled circuits. What is resonance? Resonance is a phenomena at which inductive reactance is equal to capacitive reactance, that is XL equal to XC. So it is a phenomena. And at resonance, the total impedance will be minimum and the circuit will act as a pure resistive circuit. So we have inductance, capacitance, both the inductance and capacitance will cancel out at resonance and the circuit will behave as a pure resistive circuit. And therefore at pure resistive circuit the power factor will be unity. And the frequency at which resonance occurs is called resonant frequency. And the resonant frequency, the derivation is here, which starts at the condition of resonance XL equal to XC, and we know that XL equal to omega into L, XC is equal to 1 by omega C, and by simplifying these equations we will get FR. FR is the resonant frequency. FR is equal to 1 by 2 pi root LC. Let's solve a problem. A resistor of 5 ohm, an inductor of 0.02 Henry, and a capacitor of 5 microfarad are connected in series. Find the resonant frequency and power factor at resonance. We know the formula for resonant frequency. Fr is equal to 1 by 2 pi root LC, and these are the given datas. Simply substitute the datas in the formula, and we will get Fr is equal to 503.292 Hz. Okay, and the power factor, since at resonance the circuit behaves as a resistive circuit, the power factor will be unity, that is cos theta is equal to 1. Let's solve another problem. A series RLC circuit has resistance 30 ohm, inductance 80 millihenry, and capacitance 80 microfarad. Find the resonant frequency, obtain current, power, and voltage drop across the various elements if the applied voltage is equal to 150 volt. Right. So first they have asked to find the resonant frequency. We know the formula for resonant frequency, which is Fr is equal to 1 by 2 pi root LC. And from the given data, we know the L is 80 millihenry, C is 80 microfarad. Just substitute the values, and you will get resonant frequency is equal to 63 Hz. Next, current. So by Ohm's law, we know that current I is equal to V by R. Since it is pure resistive circuit, we can use this formula. And voltage is given, which is 150 volt. Resistance is 30, so the current is 5 amps. So we have found the current. Next, we are supposed to find the power. Power is equal to VI, V is equal to IR. Therefore, P is equal to I square R. And we know the value of I, which is 5. Therefore, 5 square into R is 30 ohm. So when you substitute the value, you will get 750 watts. Next, we have to find the voltage across each element. We have resistor, inductor, and capacitor. Both are connected in series. Therefore, we are going to find the voltage across resistor, voltage across inductor, voltage across capacitor. So voltage across resistor V is equal to I into R. We know the value of I and we know the value of R. Substitute and we are getting 150 volt. So voltage across the resistor is 150 volt. Next, voltage across inductor VL is equal to I into XL, right? So in resistor it is I into R. In inductor it is I into inductive reactance. Okay, XL means inductive reactance. So I into XL. XL is nothing but omega L. Omega L means 2 pi FL. So XL is equal to 2 pi FL. So I into 2 pi FL. We know the value of I. 2 pi are constant, F is frequency, that is resonant frequency, L is given inductance. Okay, so just substitute the value and you will get VL is equal to 158 volt. Next, voltage across the capacitor. Similarly, VC is equal to I into XC. XC means capacitive reactance. Capacitive reactance is 1 by omega C. Therefore, 1 by omega means 2 pi F. So 1 by 2 pi FC, and we know the value of I. 2 pi is constant, F is resonant frequency, capacitance value is given. So just substitute and we will get VC is equal to 158 volt. The same kind of tutorial problem, similar problem, only the data has been changed. So a series RLC circuit with R is equal to 10 ohm, L is equal to 10 millihenry, and C is equal to 1 microfarad has an applied voltage of 200 volt at resonant frequency. Calculate the resonant frequency current in the circuit and voltage across the elements at resonance. Okay, so it's a similar problem we have solved just now, and in this problem we are going to solve the same way. Calculate the resonant frequency. So resonant frequency FR is equal to 1 by 2 pi root LC. From the given data, we can write the value of L and C. Substitute, you will get 1591.5494 hertz. Next, we are going to find the current. So we know that current is equal to I is equal to V by R. Since it is a pure resistive circuit, we are following this formula. And V is equal to 200, which is given. R is also given 10. Therefore, I is equal to 20 amps. Right here, the power is not asked. Therefore, we can find the voltage across resistor, voltage across inductor, voltage across capacitor in a similar way. Voltage across resistor is equal to V is equal to I into R. So I is equal to 20 amps, R is equal to 10. Just multiply, you will get 200 volt. Voltage across inductor, VL is equal to I into XL. XL means inductive reactance. And this XL is equal to omega L. Omega L is equal to omega is 2 pi F. Therefore, I into 2 pi F into L. Okay, so 2 pi F means 2 pi is given. F is a frequency, that is resonant frequency we have found, and L is given 10 millihenry. Substitute the values and you will get VL is equal to 2000 volt. And the next one is voltage across capacitor, and for that the formula is I into capacitive reactance XC. XC is equal to 1 by omega C. Omega is 2 pi F, and therefore substitute the values of F and C and simplify, you will get VC is equal to 2000 volt. Next we are going to discuss about coupled circuits. Coupled circuits. Two circuits are said to be coupled when energy transfer takes place from one circuit to other when one of the circuit is energized. Mostly in coupled circuits, they are physically not connected, but electrically or magnetically it will be coupled. Okay, when two coils are placed nearby, so here see when two coils, inductive coils are placed nearby, and the current passes through any one or both the coils, they are magnetically coupled. So it is not physically connected, but they are magnetically coupled because of the magnetic field. Then the coils are said to be coupled circuits. Now we are going to derive the expression for self-inductance, mutual inductance, and the coefficient of coupling. So first we will discuss about self-inductance. Consider the coil of n turns. So this is coil which is having n number of turns, and it also carries the current I. Flux phi is the flux produced in Webers. So the current carrying conductor produces its own flux. Therefore, phi is the flux which is produced and its unit is in Weber. If the current I changes, the flux also changes. So current, if it is sinusoidal supply, then the current will vary with respect to time. At the same time, the flux will also vary. So by Faraday's law, change in flux induces EMF in the coil. So that is as per the Faraday's law. Therefore, it is written as E is proportional to d phi by dt. Okay, so when there is change in flux, induced EMF will also changes, and E is equal to minus N into d phi by dt, because N is the proportionality constant, that is number of turns. That is number of turns. N is number of turns. So E is equal to minus N into d phi by dt. The negative sign indicates that the EMF induced is opposite to the flux causing it. Okay, so that is why it is negative. Now, the induced EMF is also proportional to the rate of change of current. So earlier we have seen it is proportional to the rate of change of flux, but now the flux is proportional to the rate of change of current. Therefore, we can also write the induced EMF is also proportional to the rate of change of current causing the flux. Therefore, it can be written as E is proportional to d phi by dt, and E is equal to minus L into di by dt. So L is the proportionality constant. Okay, L is inductance, and in the inductance the current will be flowing. Therefore, L into di by dt, where L is the self inductance of the coil. The negative sign indicates that the EMF induced is opposite to the current causing it. Okay, right. And next, equating 1 and 2. That is the first one. That is this one. What is that? The rate of change of flux and is equal to rate of change of current, that is minus N into d phi by dt, is equal to minus L into d phi by dt. Equating these two equations, we will get N into d phi which is equal to L into di, and simplifying this equation we will get L is equal to N in phi by I. This is for constant permeability. That constant permeability means d phi by dt, which is not varying. Okay, so at that particular instant or at constant permeability, L can be written as N phi by I. Therefore, the self-inductance of the coil is defined as the flux linkage, which is N phi, produced per unit current in the same coil, and the unit is Henry. Mutual inductance. Here we will be using two coils. Okay, N1 is the number of turns in coil 1, N2 is the number of turns in coil 2. So let N1 be the number of turns in coil 1, N2 be the number of turns in coil 2. If a varying voltage source V1 is connected to coil 1, so this is V1 and we are connecting this supply to N1. Okay, that is coil 1, and coil 2 is left alone. There is no supply in the coil 2. Okay, and since the voltage source is varying, it produces varying current. Okay, the current will also be varying, the flux will also be varying. The varying current produces changing flux. Thus the flux is divided into two parts. Phi 1 is equal to phi 11 plus phi 12. So what is phi 11? Phi 11 is the part of the flux which links only with coil 1. So if the flux links only with coil 1, then it is called as phi 11. Okay, so phi 11 is the flux linking this coil alone. Phi 12 is the part of the flux which links with both the coils. So here you see, uh, if the flux links with this coil 2, then we will be calling it as phi 12. Let the induced EMF in the coil 2 be E2. Okay, because of this changing flux, EMF E2 will be induced in coil 2, and the induced EMF E2 is proportional to the rate of change of flux in coil 2, and this induced EMF will be proportional to rate of change of flux E2, and hence it is written as E2 is equal to d phi 12, because 12 is the part of the flux which links both the coil, and which is equal to minus N2. N2 is the number of turns. N2 d phi 12 by dt. Therefore, here we are giving the supply to coil 1, and because of this supply, that the time varying flux and the time varying current produces its induced EMF in coil 2, and that is the expression for induced EMF in coil 2 due to the supply voltage in coil 1. Now the induced EMF is also proportional to the rate of change of current. Earlier we saw the induced EMF is proportional to the rate of change of flux linking the coil 2. But now it is also proportional to the rate of change of current causing the flux phi 12. And the current causing the flux phi 12 is I1. So because of I1, we are getting this phi 12. Therefore, the equation will be E2 is proportional to d I1 by I dt. I1 is the current flowing through coil 1. And the proportionality constant now will be M. M is the mutual inductance. Therefore, E2 is equal to minus M into di1 by dt. And now equating the two equations. That is, what are the two equations? Rate of change of current, rate of change of flux. So this is rate of change of current and this is rate of change of flux. So we are equating these two equations. Minus N2 d phi 12 by dt is equal to minus M di1 by dt. Right? When simplifying this equation, we will be getting mutual inductance M is equal to N2 into d phi I2 d phi 12 divided by di2. Okay, so at constant permeability means this d phi by d I becomes phi by I. Okay, so at the constant permeability, M is equal to N2 into phi 12 divided by I1. So this is the equation for mutual inductance. Okay, now look at this diagram. Earlier we have given supply to coil 1, and we have derived the expression for mutual inductance. Now in this circuit we have given supply to coil 2, and because of coil 2, I2 will be the current flowing through the circuit, phi 2 will be the flux linking this coil, and phi 21 will be the flux linking the coil 1, and this this flux linkage is due to I2. Okay, and the similar way of derivation has to be followed. And if you follow the similar way of derivation, the mutual inductance will be derived as M is equal to N1. N1 is the number of turns in coil 1. D phi 21. D phi 21 is the flux linking the coil 1 because of coil 2. Okay, and divided by di2. I2 is the current flowing through the coil 2, and that is the expression. And if permeability is constant, then mutual inductance can be derived as M is equal to N1 phi 21 divided by I2. Thus, mutual inductance is defined as the ability of varying current in one coil to produce an induced EMF in another coil. Okay, so one coil, current in one coil produces induced EMF in the other coil is the mutual inductance. Okay, and its unit is Henry. It is also defined as flux linkage of the flux linkage of one circuit per unit current. Flux linkage is N into 5. Okay, per unit current. Current is the denominator. So therefore, per unit current in the other circuit. Okay. Coefficient of coupling K. It is also called as magnetic coupling. It is defined as the fraction of total flux produced by one coil linking the other coil. Therefore, K can be written as phi12 divided by phi1, and it is also equal to phi21 divided by phi2. Okay, and we know that the mutual inductance M is equal to N2 phi12 divided by I1, and M is equal to N1 phi21 divided by I2. Okay, next we are going to simplify to find the value of M. Okay, so multiplying both M square is equal to, you will get, we are going to multiply these two terms. So this is the multiplication, and by simplification, we are going to use 512. Okay, 512 means from this expression we can write 512 is equal to K into 51. So 512 is equal to K into 51, and 521 is equal to K into 52. 521 is equal to K into 52. Substitute these two values in this equation. Therefore, M square is equal to N2. This K51 is substituted for 512, and K52 is substituted for 521. And in the denominator, it is wrong. It is I1 and I2. It is not I2, I2. It is I1, I2. Okay, so next, by simplifying, we will be getting that self-inductance. So here you can see N1 phi1 by I1 is a self-inductance L1. N2 phi2 by I2 is self-inductance L2. Therefore, M square is equal to K square L1 L2. Okay, taking square root on both the sides, we will get M is equal to K into root of L1 L2. And from this equation, we know we can derive the expression for coefficient of coupling K. So K is nothing but M into M divided by root of L1 L2. And this value of K depends upon the spacing between the two coils. So here we will be dealing with the two coils, and if the spacing between the two coil increases, the coefficient of coupling will be decreasing, because when the space increases, the flux linkages will be weak, therefore it decreases. So, and K is always positive, and its maximum value is 1. So its maximum value is 1. Therefore, the maximum mutual inductance occurs when K is equal to 1. So from this equation here you can see M is equal to K into L1 L2. So K, the maximum value of maximum mutual inductance occurs when K is equal to 1. So put K is equal to 1, and M max will be root of L1 and L2. Okay. Right. For analyzing the coupled circuit, we are going to follow dot rule. So what is dot rule? Let's assume that the current is flowing like this. Okay. So the current is flowing like this means, see, the current enters the coil through the dot. Here also the current enters the circuit through the dot. So both the current enters the circuit through enter the coil through the dot. Then at that condition, M is positive. Okay. And now let's assume that now let's assume that now let's assume that the current is flowing like this. In this direction, you can see here the current leaves the coil through the dot. Here also the current leaves the coil through the dot. So at this condition also, the M is positive. Therefore, this is the statement. If both the current enter or leaves the coil through the dotted end, then the sign of mutual inductance M is positive. Okay. And there is another condition. What is the next condition? Assume that one current is entering and the other current is leaving. Okay. So here you can see that the current enters the coil through the dot. Here the current leaves the coil through the dot. Therefore, the mutual inductance M will be negative. Okay. So these two rules are the dot rules, and this helps to analyze the coupled circuits. Conductively coupled coils. So we know that two coils can be connected for coupled circuits. So two coils of self-inductance L1 and L2 and having the mutual inductance M between them can be connected in four ways. There are four ways of connections if the two coils having self-inductance and mutual inductance. So the first one is series aiding, second one is series opposing, third one is parallel aiding, fourth one is parallel opposing. Series aiding. So here you can see the circuit of series aiding. The current direction is given, and from the current direction we can see that the current enters the coil L1 through the dot. At the same time, the current enters the coil L2 through the dot. So both the currents are entering. Therefore, the sign of the mutual inductance will be positive. So there are two M. Okay, one is due to this L1 and another M is due to this L2. Therefore, the equivalent inductance is equal to L is equal to L1 plus L2 plus 2M. Okay, so we have to remember this expression for solving problems. Series opposing. So here you can see the circuit, then the current direction. In the series opposing circuit, the dot you have to place the dot in similar way like this, and the current is flowing into the coil L1 through the dot, but here for coil 2 the current is leaving the coil through the dot. So one side it is entering and another side it is leaving. Therefore, the sign of the mutual inductance will be negative, and the equivalent inductance will be L is equal to L1 plus L2 minus 2M. So remember this expression to solve the problem. Similarly, for parallel aiding and parallel opposing, these are the expressions. Okay, and for parallel aiding, the circuit will be like this. Okay, parallel aiding means both the current enters the coil through the dot. Parallel opposing means it will be one current enters the coil through the dot and the other current leaves the coil through the dot. And similarly, the expression will be modified like that. Okay, L equivalent equal to L1 L2 minus M square divided by L1 plus L2 minus 2M, and for parallel opposing L equal to L1 L2 minus M square divided by L1 plus L2 plus 2M here. That is the only change. Okay. Let's solve the tutorial problem. Two coupled coils of self-inductance L1 is equal to 2 Henry, L2 is equal to 4 Henry are coupled in series aiding, series opposing, parallel opposing. If the mutual inductance is 0.5 Henry, find the equal inductance in each case. So here the given data are L1 is equal to 2H, L2 is equal to 4H, M is equal to 0.5H, and they have asked to find the mutual inductance, so equivalent inductance of series aiding, series opposing, parallel opposing. We know the formula for series aiding, that is L equivalent is equal to L1 plus L2 plus 2M, and it is given L1 is given, L2 is given, M is given. Just substitute the values and you will get L equivalent equal to 7 Henry. Next, series opposing. We know the formula for series opposing, which is L equivalent is equal to L1 plus L2 minus 2M. Substitute the values of L1, L2, M, and you will get L equivalent is equal to 5 Henry. Similarly, for parallel aiding, L equivalent is equal to L1, L2 minus M square divided by L1 plus L2 minus 2M. And substitute the values of L1, L2, M, you will be getting 1.55 Henry. And for parallel opposing, substitute the values of L1, L2, M, we will be getting L equivalent is equal to 1.1071 Henry.